Okay, cool. Hi, everyone. Can you guys hear me? Because I can hear myself. Good. So I'm really excited because we have Netflix on stage with us. They're an end user for Virtual Kubelet. But I'm going to go through an intro first. But first, to introduce myself, my name is Ria Bhatia. I'm a program manager at Microsoft. I am one of the maintainers of Virtual Kubelet. And here's Sargun. Wait, don't take that. I lied.
Sargun Dhillon. I work at Netflix on Titus, our container runtime, and I'm a senior software engineer.
Cool. So to get us started, a little bit of history about Virtual Kubelet. It started off as a small project, actually just an experimental project by Brendan Burns at Microsoft. And we basically were just playing around with what it meant to make Kubernetes more flexible, because a node in Kubernetes is inherently not very flexible. So that's where we started. And it was actually called the ACI connector a long time ago. And before KubeCon in December 2017, I want to say, we decided to make it open, and we decided to make it pluggable. So anybody that had a use case for Virtual Kubelet or like the concept of making the kubelet more flexible in Kubernetes could actually use this project past just Microsoft. It actually started out as a TypeScript project, and then we rewrote everything in Go, presumably to make it more friendly, to get more developers in the project. I think it worked. I don't know if you guys want to work in TypeScript, but we could probably do that too in the future. Probably not. Yeah, but that was the room that we all worked in. We hacked on it. There's Eric, who's over here. He was also one of the core people in the beginning to help us start the project. Okay, so what is Virtual Kubelet? So Virtual Kubelet, we don't replace the kubelet, but what we've done is inherently make it more flexible for you. So for example, one use case, and I'm going to make it really abstract so it makes sense. If you wanted to order pizza, for example, and you wanted to create a provider that ordered pizza, you could do that with Virtual Kubelet. So anytime you created a pod against the Virtual Kubelet node in your cluster, it would spin out and actually call Domino's and get you a pizza. So that's how abstract we've made the node. If you know how to fill in the functions of creating a pod, deleting a pod, and updating a pod, you can basically create a provider for Virtual Kubelet. And that could be anything from ordering a pizza to turning on the lights in this room. It's really, really flexible in that case and super easy to get started. And these are the things that we've built into it. So you can get pods, you can get pod status, you can update the pod, you can create a pod. And we also have some loosely defined capacity like restrictions around it, because we don't actually need to make a restriction. So the restriction's like 1 terabyte of memory and things like that. But that's because we're not an actual node. We're just sending out API calls to whatever is in the backend. So whether it's Domino's, whether it's Azure, whether it's Amazon, whatever it could be, all we're doing is just transferring information from Kubernetes to that actual backend service. All right, so the anatomy of the node today, and I'm going to step in front of here just so I don't miss anything. So the node inherently comes with a lot of constraints, and that's what we set out to solve. How do we make a node more flexible? How do you have an unbounded amount of resource and things like that? And there's a lot of constructs of pods actually getting scheduled out to nodes that we also needed to figure out within Virtual Kubelet. So when you schedule a pod to a Virtual Kubelet node, we actually changed the way that you have to interact with the node itself. So you don't lie within the same capacity restraints because you're not actually in the cluster. So a lot of the pods that we're spinning out are actually backed by a different service, and they're not in your Kubernetes cluster at all. Okay, and this is another slide to show you what the node does today. We're continuously in Kubernetes getting, we have control loops to basically get container logs and get status and things like that. This is something that we've replicated in Virtual Kubelet, but we have a smaller set of things that we've replicated in Virtual Kubelet itself. And what is Virtual Kubelet? So Virtual Kubelet treats the concept of pods and nodes in the abstract, just like what we talked about before with Domino's. It's an unbounded, a node is a bounded amount of resource, but Virtual Kubelet itself is not. We have a lot of common code in the VK in Virtual Kubelet. Well, we don't have a lot of common code, but that's where providers come in. So you actually get to define how networking works. You define how creating a pod works, how updating a pod. We just give you a library which you fill in on your own. And we also have a community that can back you up and help you write your own providers. And Virtual Kubelet itself can actually be deployed as a pod. So that's what we do in Azure today. We're deploying Virtual Kubelet as a pod, but it looks like a node in your cluster. But if you go into your kube system namespace, you'll be able to see Virtual Kubelet as a pod. Cool, so why Virtual Kubelet? We have a bunch of different use cases, one of them being the bursting use case, so being able to burst into a different service, so you don't have to use the capacity within your cluster, you can burst out somewhere else. We also have some IoT use cases, if you want to basically represent a Virtual Kubelet pod as an IoT device and things like that. And then also just an alternate kubelet. And we'll probably get into that a little bit later. And this is a shout out to the Azure folks, and this is something that I worked on in the beginning, so I kind of wanted to show off the Virtual Kubelet bursting use case, where basically you have a defined pool of resources within your VMs, and you use Virtual Kubelet to spin out into something called Azure Container Instances. And if you want to learn more, come to our deep dive session this week on Virtual Kubelet, and then I'm going to hand it off to Sargun.
Great. So I'm going to be talking about changing the engines out in flight and how we adopted the Virtual Kubelet for utilization in production. The system I'm going to be talking about is called Titus. Titus is the primary container runtime that's used at Netflix. It's used for all sorts of applications at Netflix, from big data workloads like Presto to our online streaming service. So if you've used Netflix on your phone, you've probably used Titus, to our media encoding engine. And the project was started in 2015. In 2015, the container runtime landscape was pretty significantly different. For one, Kubernetes was only about a year old, and it hadn't really become the ubiquitous cluster manager that it has become today. And when we started the project, we weren't really sure whether this was going to work or not, so we wanted to try to leverage as many off-the-shelf technologies as possible. In leveraging those technologies, we decided to use Docker as our container runtime, Mesos as our cluster management and resource management layer, and gRPC and protobufs for API definitions. The team that works on Titus is relatively tiny. Today we're an 11-person team, and about 2 years ago we were a 6-person team. We develop, operate, and support the product. We're on call for it. We have to provide user support. And given that we're such a lean team, we have to make our decisions relatively conservatively. And in that, when we adopt new technologies, we like to move iteratively as opposed to make big jumps. About a year ago, we decided to open source all of this code. And what I'm going to be talking about today is mostly in the open source now. The Titus architecture is a little bit different than what you have in a traditional Kubernetes environment. The Titus architecture works with the Titus API fronting it. The Titus API has many concepts that are very similar to AWS concepts, because most people at Netflix are used to AWS concepts. So we have the idea of a job, which is very similar to an ASG, and the idea of a task, which is very similar to an instance. In addition to this, the Titus API has many references to actual AWS constructs like ALBs, like autoscaling groups, etc., because we try to mirror these concepts as closely as possible, or even push responsibilities as much as possible onto AWS. Behind that Titus API, we have the Titus master. And the Titus master is responsible for orchestrating the cluster. And it has the source of truth of the cluster that it stores inside of Cassandra. And it forces down all of the state of the cluster into Mesos. And Mesos is then responsible for farming it out to all of the agents and getting them to converge on the intended state of the cluster. Diving a little bit deeper into the Titus agent architecture, today we use, or previously we've used Mesos agent, and Mesos agent has run the Titus executor. And the Titus executor is effectively our own, you can think of it as like a provider where it talks to Docker, it spins up containers, and it manages that container lifecycle. So what's missing in this architecture? It's lasted us a few years now, it's in production, and we were pretty happy with it. There's a couple things that we wanted. One of these was a northbound API. So the idea that pods and nodes could signal upstream what their status is. We've actually talked about this in our blog, in the blog post of using predictive CPU scheduling for opportunistic workloads, because nodes know more about their state than the cluster control plane does. For example, a node can analyze its workload and say, I have 4 free CPUs available, and change its node status to say this. The other aspect is extensibility. The fact that the downstream API can include anything like an IAM role or various metadata about the pod, allows us to go ahead and monitor that information and act upon that information intelligently. Previously with Mesos, the answer for this was to write a custom C++ module and do a bunch of awkward stuff to make it work, whereas Kubernetes has some better solutions for this. And at the end of the day, we wanted to leverage custom data. We wanted to be able to leverage CRDs, and we wanted to leverage config maps and other objects in order to instrument our system, in order to go ahead and experiment with our system. And lastly, the vibrant community. We saw what the Kubernetes community was doing and what all of you out there have been developing, and we were kind of jealous. Like, we wanted access to this. So that left us Kubernetes curious. And we wanted to see whether we could start to leverage parts of Kubernetes in our ecosystem or in our environment. So we looked at the typical Kubernetes architecture. And in the typical Kubernetes architecture, instead of having a separate API and control plane, instead everything is built around the API server. And all of your clients go ahead and talk to the API server and whisper in your objects around replication sets or stateful sets, et cetera. And then you have controllers that go ahead and act on these objects to go ahead and create the pods inside of the API server that then the kubelet is responsible for converging the state upon. If we look at the typical kubelet, the kubelet does have a level of modularity. The level of modularity in the kubelet is built upon the idea of using the CRI, the Container Runtime Interface. And the Container Runtime Interface allows people to drop in replacement container runtimes and run their own containers with these container runtimes. And it has two other large portions of pluggability, CSI, the Container Storage Interface, and CNI, the Container Network Interface. And as long as you conform to the idea that the kubelet uses to build up pods and build up containerization environments, you can go ahead and implement a CRI-compliant runtime and get all of the features and the capabilities that the kubelet gives you. So we had a couple options forward with this, and a couple options to decide how we wanted to start to adopt Kubernetes. The first option was to leverage pure Kubernetes with Kubernetes controllers. And this is how a lot of the community runs Kubernetes. It's a simple architecture. It works for most people. But Titus has grown over the past couple years to become a fairly large portion of our fleet. And in that, we have a lot of our users inside of Netflix that are used to that Titus API, and asking those hundreds of users to move over to a new API would probably be a little bit difficult. The other aspect is that we wanted to use as many components as we had today because we were operationally used to them, and we knew how to run them at scale. So the other approach is to run API server as a replacement to Mesos. This is nice because it's a small incremental change. It involves replacing one component. The other aspect is that it doesn't require those hundreds of callers to move over. The downside of this is it's an unproven path. And not only is it an unproven path, the kubelet itself isn't meant to absorb pods really from like arbitrary pod providers or have a lot of the information that we were able to pass in to the containerization platform previously. In addition to that, the other aspects are that Titus has some different concerns in terms of security and in terms of isolation that the typical architecture did. For example, we care a lot about security in terms of container breakout. We care a lot about isolation in terms of performance. So with this architecture, we decided to go down the route of using API server as a drop-in replacement for Mesos and running this thing that we've decided to call Titus Kubernetes. In Titus Kubernetes, what we do is we have the Titus master. And the Titus master, all it does is it pushes pods down into API server. And then API server only runs a subset, or runs with a subset of the controllers that you typically have in a Kubernetes architecture. And these are just your basic things to maintain your namespaces, to maintain pod GC, et cetera. And then this gets pushed down to the agent whose job it is to eventually converge upon the state that the Titus control plane has whispered down into API server. And these controllers are things that we largely have already implemented. So we already have implemented things like resource quotas into the Titus master, a horizontal pod autoscale in the Titus master, and the idea of a cloud controller. And these are the proven components that I was talking about earlier. Not only this, but we also have components inside of the rest of the ecosystem, like Spinnaker that does deployments, and that does config management for us. So what about the agent? How do we move forward with the agent, given that this is how we move forward with the control plane? So we asked ourselves, what if we just implement CRI? What if we just implement that API that I was talking about earlier, that anyone can go ahead and drop in a replacement modular interface? Well, first you have to understand what we were working against before. We were working against the Mesos API. And the Mesos API is a much smaller footprint and a much less opinionated API. It effectively has two callbacks, launch task and kill task. And in that, it basically passes you some bytes that are from the control plane, and you get to decide whatever you want to do with them. It's not particularly opinionated on what's in that. It can be a pod, it can be a container, it can even be a Spark job. On the other hand, this is the CRI API, and this is only a subset of the CRI API. The CRI API is incredibly opinionated about how backends have to work based on the composition model that it dictates. And that composition model is built around the idea of pods. And although that composition model is super powerful, it's also fairly complicated, and it had a lot of cost for us to move over to. And part of this cost comes from the fact that the Titus executor actually implemented a lot of aspects that the kubelet was responsible for in a CRI world. Because we talked directly to Docker, we were responsible for much of the container orchestration in terms of starting up the container, creating the container, and image management that the kubelet is typically responsible for. And we wanted to keep this code given that we knew how it worked and it had been operationalized at our scale. In addition to that, we had built up our own networking plugins and our own storage plugins that didn't really jive in the world of CNI and CSI, and the cost of moving these over was unknown at the time. We also had our own container composition model that wasn't pods. Instead, we relied on this idea of system services, where the actual executor was responsible for injecting in the sidecars that ran alongside the user's code. The only real thing that we were missing that the kubelet implemented was cgroup management and being able to make sure that the container is torn down at the end of the executor's lifecycle. So our other question was, what if we just implement a Kubernetes API client? What if we go ahead and we talk directly to API server, and we go ahead and have all the behavior of converging the state of the node ourselves? And this is where we realized everything that we have missing inside of the Titus executor. The Titus executor delegated the idea of node registration to the Mesos agent. It delegated that reconciliation model of when the system comes up from fresh or when the system comes up from failure to the Mesos agent. And it left state caching to the Mesos agent. And this is where virtual kubelet came in. Where virtual kubelet effectively takes the API server's model of a declarative API saying, this is what you should be running, to pushing that down to an imperative API. And where you can implement the callbacks to say, let me actuate your system to say, run this task or shut this task down. In addition to that, virtual kubelet makes it so that you don't have to do a lot of the heavy lifting that you traditionally have to do when you're implementing an API server client. Like, for example, it does state caching. It does secret caching, and it has config map caching. So you don't have to implement a lot of this, what we'll call undifferentiated heavy lifting. It also implements a reconciliation model that's been proven by a bunch of folks and been operationalized by a bunch of other folks, rather than having to have us figure out how to implement this and step on all the potential landmines that are out there. In the virtual kubelet API, the callbacks that Ria was talking about are really similar to the Mesos callbacks. The Mesos callbacks are launch task and kill task, whereas the virtual kubelet's APIs are create pod, delete pod, update pod. And if you want to implement reconciliation, you have to implement get pod, a couple APIs. And virtual kubelet really doesn't care what's inside of that pod specification. In fact, we were able to move over by simply taking the Mesos container info that we had before and encoding that as a base 64 value and stuffing that in the pod and saying, this is going to be our pod spec. We're going to kind of ignore all of the fields that Kubernetes is super opinionated about and instead overload those with our own specifications of what image we're using or what resources we're using. For example, we have this idea of two-level resources, where resources can specialize, and that's not really something that's implemented via scalar resources. So instead, we were able to leverage virtual kubelet and pass down these opaque resources through the pod specification. Lastly, the transformation of that declarative API is really important to us because for every Titus executor to have the knowledge to converge upon a given state would have been cumbersome. And being able to delegate that to a library is a separation of concerns, so you can let a shared system do this. And this is how we came up with the Titus virtual kubelet architecture, where our implementation of the virtual kubelet goes ahead and uses systemd as a replacement to the responsibility that kubelet was previously performing to create and destroy C groups. In those C groups, we run the Titus executor. And this is the exact same code that we were able to run in our previous architecture without having to change any lines of code. And then that can go ahead and talk back to Docker and run the user container. And this was really appealing to us because it meant that we could run almost all the same code that we previously ran and we previously operationalized. And for the team, at 11 people, we didn't have to retrain everyone on how the system runs differently on Kubernetes versus on our legacy architecture. And as a cluster, what we can do is we can run an instance of Titus Virtual Kubelet on every instance inside of our clusters. And then these can go ahead and spin up Titus executors underneath them, and we can re-roll these in flight. So the virtual kubelet library has features to be able to do in-place restart and in-place reconciliation. So what about the transition? We obviously couldn't say, hey, everyone, shut down your pods, shut down your clusters, and move over. We had to have a federation solution. And that's where Titus Federation came into play. And what Titus Federation is it's a mechanism by which we can use to route different workloads to different cells. In each region, we have about 2 cells today, 2 to 3 cells, and we split workloads in order to scale Titus. Because we know how much scale a given cell can handle, we can basically rely on this information to say, let me go ahead and take you to the next chunk of reliable scale by adding another cell. We have a look-aside table that says, based on some routing rules, dispatch this workload to a cell. And we were able to leverage the same capability to say, hey, your workload is a little bit more tolerant to things, therefore we can route you to the Kubernetes cluster earlier rather than a very high-risk workload. And then on the read path, it can take the view from our Kubernetes cells and our Mesos cells and combine these into one global view of the system. So what we were able to do in transition was run the stack with Mesos and run the stack with Kubernetes side by side under Titus Federation. And our users were able to continue to speak the same API that they were speaking to before, where they had these models that were very similar to AWS models. And this is something that we've been able to prove at some level of scale. This is one of our clusters that effectively runs production-like workloads. And this is a graph of container starts per second, where the green line is the number of container starts per second on the virtual kubelet, and the red line is the number that were on Mesos. And we were able to effectively switch users in flight without any of them noticing that the underlying architecture had changed out. So what about the challenges? This project had, challenges like every project does. The first aspect that was difficult was the lack of documentation on controllerless Kubernetes. The fact that we were running Kubernetes in kind of an odd way, and that virtual kubelet let us do a lot of stuff that you wouldn't traditionally have the ability to do in a controller Kubernetes world, meant that we had to effectively run the kubelet and figure out what the kubelet was doing in order to determine what the behavior that the virtual kubelet should do or the Titus virtual kubelet should do. And really that boils down to the lack of a formalized container state machine. So what we ended up doing in order to solve this problem was we ran the kubelet and we simulated a bunch of state transitions, and we figured out what the kubelet was doing and made the virtual kubelet act in the same way. And that kind of became like a running thing where rather than having any kind of documentation to look towards, the solution was to look towards the the code in the kubelet as a formalization of the specification. So what about the future? One of the things that we've considered is moving more and more state to the API server and saying, maybe have like jobs in the API server, or maybe having more configuration information inside of the API server. The other aspect that we've considered is how do we scale out API server, and can we leverage VK to scale out the API server, of saying have one VK that registers in multiple API servers and combines this data together, or alternatively even having a VK that represents multiple API servers underneath it or multiple clusters underneath it. Lastly, the flexibility that the VK gives us is immense. And we've thought about adding new executors to the virtual kubelet. For example, the ability to add a Firecracker or gvisor-based executor would give us the ability to run containers in greater isolation, rather than having an environment where we're using Docker that has lesser isolation. And that is the Titus virtual kubelet. Thank you.
I think we ended a little bit early, so we can take some questions now, and you might get a sticker if you ask early. Do you have one? Good. He's going to come with a mic, too. That was great.
Thanks.
So you have said that we can use the pod abstraction to express pretty much anything, which I understand that this does not need to be necessarily workloads as we know them with standard Kubernetes. You use the example of ordering pizza.
Yeah.
The question is, Kubernetes, like the upstream Kubernetes, is pretty strict about the schema of the pod template of the pod spec. So how do you create your own custom schema for a pod spec?
For a pod spec?
Yes.
We basically take in the same pod spec that Kubernetes does. It's still Kubernetes that's delegating the workloads to the node specifically. So it's still Kubernetes that's scheduling it out, so it still needs to understand the same things. And we take in, so what we've done on the provider side is we'll take in the same, like, if you have a CPU constraint, it's up to the provider itself to write that in and take it in. But if you do write it in, it's not going to stop you from scheduling out to the virtual kubelet node. It just probably won't work as expected.
So it means that the schema of a pod spec for like any abstraction that I can think of needs to be the same schema that's for regular pods.
Yeah, and that's it's really, we put a lot of that work, and I'm talking from like a maintainer of virtual kubelet, we put a lot of that onus on the actual providers themselves. So you will implement as much of the pod spec as you want to, and you'll figure out what it means in terms of consumption and in terms of what a pod image would mean and things like that. But for Kubernetes to schedule out, it does need to have some sort of aspect of a pod.
Got it. Thank you.
I mean, to expand a little bit upon that, Titus solves this problem by basically taking all of our custom information and just stuffing it into object meta as a base 64 encoded string. Excuse me? Yeah, as an annotation. And in doing this, we were able to move over our legacy schema over to virtual kubelet without having to figure out how to map things like image and map things like resources, because the resources model that we had previously was a little bit different.
Yeah, so I think this and the Netflix use case is definitely a good one to demonstrate the uses of the virtual kubelet by showing how to adapt existing software platform, right, using the other technology and into the Kubernetes and the platform. You also discussed the trade-off between different options. I was just wondering if, generally speaking, in the general cases, if I build something from scratch, so what's the good user cases? Still useful using the Kubernetes? Also, if you look at the long-term, right, and maintenance, other thing, so you think this kind of the solution, by introducing the Kubernetes, virtual Kubernetes, still a good solution from the long-term perspective? Or why don't we just have a purely Kubernetes and the native solution? Thank you.
So for us, we had a couple of things to consider. We had the immediate world to consider of Do we spend a bunch of time transitioning to a code base which, although people run at a relatively large scale, don't run in an environment that's exactly like ours? And the other aspect was, how long do we want to spend migrating our code? There was the slide earlier that I had that showed the overlap between components that the virtual kubelet, or excuse me, that the Titus executor implemented and the kubelet implemented. Now, we could spend all of the time to move over our code to go run under the kubelet and to go run under the Kubelet architecture, but we wanted to make an incremental decision, at the time at least, to utilize the components that we had that we knew worked, whereas the API server components that we knew that worked, and use the best of both worlds. Longer term, we might consider changing how things work, but given the different priorities we have at our scale, we would have to reconsider in the future of whether we want to move to raw kubelet or not.
Are you asking for like the general use case of virtual kubelet? I mean, if you're trying to mask different infrastructure that's not easily implemented in core Kubernetes already, that's where the kubelet would come in. Or if you're trying to spin out to a different infrastructure, a different service, and things like that. If virtual kubelet it's the solution to the problem. You wouldn't look at virtual kubelet first. You would say, hey, I have this problem. I want to use Kubernetes on top of Titus, or I want to be able to use my container instances infrastructure, but I want to use the same APIs as Kubernetes and have a cluster on this side. Or a hybrid use case could also be in this case where I have on-prem and I have on-prem cluster or nodes or something, but I also have a cluster in the cloud. I want to be able to use my same cluster, my same API to spin out to both. That's when the kubelet could be a solution for you, or the virtual kubelet. But there's a lot of use cases. So it's really like, do you have a problem? Come talk to us, and then maybe virtual kubelet's the right answer.
Do you have any examples other than the Titus virtual kubelet? And the other question I had is there the notion of a mixed mode cluster where you can use the regular pod controller and I guess like the virtual kubelet controller, or I guess it's not a controller?
Like using nodes in your cluster and a virtual kubelet node?
Correct.
Yeah, that's one of our primary use cases in Azure, actually, in a lot of the clouds, is we run in this mixed mode where we use Azure container instances, and we back that up by virtual kubelet. And then in the cluster itself, in your Kubernetes cluster, wherever it is, that's the nodes that are in the cluster. And then anytime you spin out to virtual kubelet, it actually spins out to a different service. So it looks like it's in your cluster, but actually, you don't hold any of those nodes or any of that compute.
So, perfect.
Yeah,
So,
and then the first question?
Yeah. Is there,
Wait, what was the first one? Sorry.
do you have any other examples of virtual kubelets apart from the Titus virtual?
Apart from Netflix?
Yeah.
Yeah, so one thing I didn't mention is we have a lot of providers in virtual kubelet. And so past Netflix, past Microsoft, we also have been working with Alibaba, VMware, and those are provided in HashiCorp. And these are providers that are providing services to people. In terms of end users, since the thing is, virtual kubelet's very specific in the terms of you're spinning out to a different service, correct? So what ends up happening is a lot of us have a lot of customers that we can't talk about. It's like running AKS, it's like running GKE and things like that. So yes, there's a lot of end users. Netflix is one of the only ones that have built their own provider and built it for their own use case.
Could I ask one last question?
Yeah, of course.
When would I use like a runtime class versus a virtual kubelet?
A runtime class is like a CRI implementation.
Yeah.
I think that any time where you have a composition model that's different than the CRI composition model or the kubelet composition model is one case. So for example, if you want to run virtual machines, they don't compose the same way that pods will typically compose in something like Docker or a containerd. And then the other case is where you have pods that might not really be VMs or containers at all. For example, if you want to run like a serverless function as a pod.
Cool, and I think we have time for maybe one quick question, and then you guys feel free to come and talk to us after for a couple minutes.
So the API between the Kube API server and the kubelet is not versioned and considered to be internal. Has the virtual kubelet interface ever been broken by changes that are made in core kube between the API server and kubelet?
So the virtual kubelet 1.0'd a little while ago, and in that time, we haven't seen any breaking API changes, but we would have to go ahead and mask those API changes from the provider as that transitioned. One of the aspects that kind of makes this more complicated is that not all people who are creating pods for consumption by the virtual kubelet are actually conforming to the way that Kubernetes behaves itself. At the end of the day, like, this is kind of the problem you're going to hit because you're running like a controllerless Kubernetes, and that's not one, that's not officially supported, and two, like, we're kind of reverse engineering the behavior that the current system implements and implementing it ourselves.
Thanks.
Okay, well, thank you. Thank you all for coming out. And if you want a couple more stickers, feel free to come up.